Today we're going to be learning about Newton's second law. One of the things that we know is, Sir Isaac Newton was around obviously a long time ago. He was very smart and he held a position at the University of Cambridge called the Lucasian Professor of Mathematics, and it was paid for by the King of England. He decided that, hey, this guy's a really smart guy, I'm going to pay for him to be a professor. So he was one of the first people to really have the time to start developing formalized equations for things. One of them is Newton's second law. So he found out basically two things. Number one, acceleration is directly proportional to force. He said that the harder you push on something, the larger the acceleration would go. And that symbol in the middle there means proportional. So we know that as force goes up, acceleration will go up, and vice versa. If force goes down, acceleration will go down. Another thing he kind of figured out, and this one makes a lot of sense, that as the mass of something got bigger, so if you make an object significantly larger, the acceleration would decrease. So this is called an inverse proportionality. So acceleration is inversely proportional to the mass. So that means if acceleration goes up, that means the mass would have had to go down. Like the object would have to get smaller, and that makes sense. So now we have these two relationships, acceleration and force and acceleration and mass, and Newton combined them together to get this equation. Acceleration is equal to the net force, or sum of all forces, over the mass. Now, this is the equation that he used for a long time, but over time it's kind of evolved. It's really turned into this equation. The sum of all forces is equal to mass times acceleration. And this force right here is really referring to the net force, or all the forces added up. In all the problems that we've done so far, we've called those balanced force problems because all of the forces have canceled out. In the problems that we're going to do from this point on, not all of the forces are going to cancel out. We're going to end up with a net force. So now we've got this example. I have a 3 kilogram box sitting on the ground, and it experiences a 4.9 Newton force. So I'm going to draw that force. I also have other forces that I can't forget. I have to remember about force of gravity. So I'm going to draw that as well, force of gravity. I can find that by multiplying the mass of 3 kilograms times the acceleration of gravity, which is 9.8 meters per second squared. When I do that, I get the force of gravity, or the weight of the object. It's 29.4 newtons. Well, I've got other forces. I've got an upward force. That's called force normal. Now in this case, I want to think about, is it going to cancel out gravity? Well, it should, and the reason is, if it doesn't cancel it out, that means the box would either be jumping into the air or digging a hole through the ground. So that can't be true. So we know that the normal force is also equal to 29.4 newtons. There's no friction in this problem, so I'm going to ignore that. So now when I start looking at kind of all these things, I don't know what that is. Let me get rid of that arrow. So when I look at all these different things here, I'm basically trying to figure out between this force, the 29.4 newtons, and the 29.4 newtons, what happens with those? Well, when I start investigating a net force, that means add them all together. Well, an upward force of 29.4 and a downward force of 29.4, they cancel out. So I'm left with the sum of all forces is equal to just 4.5 newtons. So I've got my net force, but I'm also solving for the acceleration. So I have an equation that says the sum of all forces is equal to mass times acceleration. So I'm going to write that out as 4.5 newtons equals 3 kilograms times the acceleration. I'm going to divide both sides by 3, and I get an acceleration of 1.5 meters per second squared. Now, this number is relatively small, but we're not pushing very hard on this box. And what we're starting to realize is, well, an acceleration is actually the link between this chapter of forces and everything we learned before that. So when you go back to our first couple weeks, distance, displacement, speed, velocity, acceleration, those are all linked. forces were unlinked until just now. Now we have a link between forces and acceleration. Now we're going to look at doing a slightly more complex problem. So what I have is a frictionless plane. There's no friction. All I have is a box. It is on, it's 30 kilograms is its mass, and I have a ramp that is at 30 degrees. So just like we've been doing all along, we're going to first draw a force diagram. So I'm going to do this off to the side. I'm going to do it over here. So first thing I want to do is, hold on. Okay, I'm going to draw my force diagram here. So here's my dot. I've got force of gravity straight down. In this case, I'm going to take 30 kilograms. I'm going to multiply by 9.8. I'm going to get a force of gravity of 294 newtons. Good, so I got one force down. The other force that I have is a normal force, and it's perpendicular to the plane, so that's my normal force. I, at this time, don't know what it is. So I've got a normal force. Again, I don't know what that number is, but it's there for now. So now what I have to do is I have to realize that I need all my forces to line up. And just like the problems we've done for a while, we're going to kind of take this, and we're going to take a dotted line and turn this into a triangle. What that triangle is going to do for us is allow us to divide this into components. So let me zoom in here. We're going to turn this into F, G, X, and F, G, Y. And again, I know this is still a 30-degree angle. So I'm getting closer now to solving this problem. And now that I know that basically I have one side here that is 294 newtons, I can now solve for those other two sides. So I'm going to use sine and cosine. So for x, it's going to look like 294 sine 30 degrees. And on my y side, it's going to be 294 cosine 30 degrees. So let's use our calculators and solve for that. So what I found was using my calculator, which I paused this, so I did it in my calculator separately. I found that in the x direction, I have 147 newtons of force, and in the y direction, I have 254.6 newtons of force. So now I kind of have enough stuff to kind of start drawing some conclusions. First thing I know is, let me go over to my picture here. In this direction, those forces are going to cancel. Like the force out of the plane and the force into the plane are going to cancel out. I know that because the box is not going to jump up in the air. It's not going to dig a hole through the ramp. So those are going to cancel out. So I found that this force down was 254.6 newtons. Well, this is going to be also 254.6 newtons. It's got to be, because it's not. They're going to cancel out. So the only force I have left over, though, is down the ramp. In this direction. That force, again, was equal to this component, the x component of gravity, and that was 147 newtons. So back in my picture here, I now know that I have 147 newtons down the ramp. And that 147 newtons down the ramp is going to help me solve this problem. So just like the last problem, our order was to divide things into components. Anything that was not up, down, left, right I had to do, which I did in dotted red there on the right. I then found the components using a calculator. The ups had to cancel the downs. But in this case, because there's no friction, there's nothing going to cancel out this force. This 147 right here is not going to be canceled out. So when I think about my net force, so my net force I found was going to be, let me write it down here. My net force is going to be equal to 147 newtons. And I'm going to use that in my net force equation of net force equals mass times acceleration. I can get 147 newtons equals 30 kilograms times acceleration. When I do that, I get an acceleration of 4.9 meters per second squared. And that's the number we're usually looking for. Some things I could ask you as an extension of that would be, and I'm not asking these for this problem, but I could ask, what's the velocity after 5 seconds? How far has it gone in 3 seconds? How long would it take to stop? This is why I can link this information to a previous problem. Okay, here's an example problem that I want you to work on now. It's very similar to the last one. I'm going to change the numbers up a little bit, but it's a very similar procedure. So I want you to work through this one, and then I'll show you the solution after that. The situation is I have a frictionless, that's important, frictionless ramp at a 40-degree angle, and I have a 9 kilogram mass on it. That 9 kilogram mass is going to obviously slide down the ramp. I want to know two things. I first want to know what is the net force, and I want to know what is the acceleration. Sorry, not that. What is the acceleration? So I'm obviously going to have to do the same steps. Force diagram. I'm going to have to do my axes, anything that doesn't line up. I'm going to have to do find the up and down parts, cancel them out, and find the part that goes down the hill. So you're going to do it in that order. I'm going to pause here and solve it after the break. Get to work. Okay, let's go through and solve it. So the first thing you're going to do is you're going to draw a force diagram. So I'm going to do that off to the side here. I've got a force down, that's force of gravity. I've got a force normal, that's at an angle. The first thing I know is that the force of gravity is equal to 9 kilograms times 9.8 meters per second squared. So in my calculator I did that and I got 88.2 newtons. Now again, I look at this and I investigate and I look at it and I say, hey, these things aren't lined up. I have to make them line up. So just like we do always, I'm going to zoom in here. I'm going to take my gravity and I'm going to divide it into a triangle. I know that this angle right there is the same as my incline. I'm going to call this FGX. I'm going to call this FGY. I'm going to solve for those two sides. So for the X side, I'm going to use 88.2 times the sine of 40. And for this side, I got 56.7 newtons. In the Y side, I'm going to do 88.2 times the cosine of 40, because it's the adjacent angle. I get 67.6 newtons. So just like I've done in the last problem, I now know that if I have 67.6 in the upwards direction, I know my normal force is going to be 67.6 newtons. Those have to cancel. So I don't really care about that or that. All I care about is this right here. So I'm going to take that number, and I'm going to say that my net force here is equal to 56.7 newtons. And then I can find my acceleration by saying, let's go back to what Newton said. Newton said it was equal to the sum of all forces over mass. F equals ma rearranged. Over 9. What I get is an acceleration of 6.3 meters per second squared. You know, even though I'm not here today, you're still, this large packet we're going to work on as the next couple days go by. So on this large packet that you're getting, you're going to work on the first page, number 1 through 7. And then on the third page, there's a pages in the lower right-hand corner. You're going to do numbers 5 and 6 in that page. Now, in that one, you're going to have to go back to some old equations. You're going to have to go back to delta x equals 1/2 at squared, stuff like that. And you're going to also have to go back to, actually, that's the only one you need. Actually, then you also need v squared equals v naught squared plus 2a delta x, if you remember that one. And then also v equals at plus v naught. So this is your homework, is to work on those 9 problems. Well, when I come back, I'll see you on Thursday. Thursday we're going to do just lots of problems. Keep working. You have a quiz on Friday. That quiz is only on balanced forces, or problems where all the forces cancel out. Some examples of that were the ones that we did pretty much prior to today. Number 7 in that packet, which we'll go over on Thursday. That whole packet that we just were working on Monday, all of those problems, ropes, find T1, find T2, find the mass, find all that kind of stuff. We'll go over those on Thursday, and the solutions to this entire packet are available online on the website. So worst case, if you're having trouble with it, you can go on there and look, send me an email, but I'll be back on Thursday to help you out. And then Friday, we've got our quiz. The quiz, again, is only on balanced forces.